Hi class, I wanted to go over a couple things with you on in Chapter 2 here and we'll go section by section. So this lecture is mainly on Section 1 and it talks about just basically what you see out in the sky and a little bit about what the ancients used to think was going on in the sky, what these stars were and where they were located. So they thought, looking out at the sky, it seemed like everything was like on this ball. It seemed like all the stars were attached to this ball and they called it a celestial sphere. And it seemed like that whole ball was going around the Earth, was rotating around the Earth, and the Earth was at the center of the ball. It just seemed sort of natural because you look up at the sky over the course of a night and everything kind of goes from one side to the other, from one horizon to the other, and you don't really notice any movement among the stars. So it seemed like everything was fixed to some big sphere centered on the Earth. And there were a few things, 5 things, plus the moon and the sun, that seemed to move differently, but everything else, all the stars, seemed to move exactly the same across the sky. So they had this idea of the celestial sphere as being this big sphere centered on the Earth with all the stars kind of stuck to it. And the 5 things, the planets, the brighter planets that we can see with our naked eye, were other things called, planet means like wanderer. The planets are just kind of wandering around in a sense, these kind of relative to the stars. Well, we know that's not quite right. The stars are not stuck on a ball, and the Earth isn't at the center of the universe anymore. So, in fact, if we look at different stars in a particular cluster or in a particular constellation, they're actually very different distances away. So this shows that these stars here look like they're in the same region of the sky, but in fact they could be very different distances away. They might be in the same direction, but one of them could be really far away while the other ones are a little bit closer. So you can have really big differences in distance between the stars, but they look like they might be the same distance. Unless you really start studying them and measuring some things about them, you realize then that they are actually very different distances away. So this ball of stars, in a sense, is still a useful model to describe the location of things. We'll put a coordinate system on here, kind of like latitude and longitude. But a couple basic reference points are this point up here, the North Celestial Pole, is a point directly above the Earth's North Pole. So here's the Earth, and the Earth's North Pole is right there. And the North Celestial Pole is directly above that. The South Pole of the Earth is on the south end here, and the South Celestial Pole is directly above that. And then there's a line on the celestial sphere that's directly above the equator of the Earth, and we call this line the celestial equator. And then if we were to plot, if we were able to see the stars during the day, if we could maybe turn down the brightness of the sun and see the stars during the day, we would see that the sun appears in different positions every day. It moves a little bit every day, and it makes its way around the celestial sphere in the course of an entire year. And so these little yellow dots are positions of the sun every couple days, every day or a couple days, and they go all the way around the celestial sphere. The constellations that the sun goes through are called the zodiac, and this line here has another name. It's called the ecliptic. So this line that the sun appears to follow across the sky relative to the other stars is called the ecliptic, and the line that's directly above our equator is called the celestial equator. And so modern day astronomers use those reference points to talk about locations of things, even if there isn't really a ball of stars out there. It's still a good reference system, good coordinate system to base measurements on. So modern astronomy also has they have official names for stars, for constellations, for things, asteroids, and so on. And so there's 88 official constellations that cover the entire celestial sphere. And you can look here that these constellations are actually a region on the celestial sphere. They're outlined, they're a particular region, not just simply a pattern of stars, but a constellation is actually a region of space on the celestial sphere. Here's another view of that, a little bit less cluttered. So here's again is the Earth. That point directly above the North Pole is the North Celestial Pole. Directly above the South Pole of the Earth is the South Celestial Pole. And because of the Earth's tilt, because of the tilt of the Earth's axis, the equator, this plane, this line that's directly above the Earth's equator, isn't lined up exactly with this ecliptic. All right. If the Earth's axis didn't have a tilt to it, then the sun would always be somewhere on this celestial equator. The sun would always go directly overhead at the equator of the Earth, and at other latitudes you wouldn't see it directly overhead. So at like roughly noon or so. So at roughly 12 o'clock noon, around that time, you would see the sun directly over your head if you were on the equator every single day if the Earth did not have a tilt. But because the Earth does have a tilt, the sun is sometimes higher, sometimes lower than the equator. And if you're on the equator, that means it's sometimes to the sometimes to the south, sometimes to the north of directly overhead. And there are some days where it is directly overhead at about noon on some of those days. Here's another view of the Earth, but now we're looking at the entire galaxy now. So we had these two reference planes or lines we could think of as the equator, the celestial equator, and then the ecliptic. So this ecliptic represents the path that the sun follows over the course of a year. The celestial equator again is just that line directly above the Earth's equator. We can also talk about the galactic plane. If we looked at our galaxy, there's a certain sort of disk. Our galaxy has a disk component to it, and there's a plane that kind of cuts through that disk, and we're in that plane. And so we're not in the center. We're about 2/3 of the way out or so, about half the way out, roughly. It's not too important that you know exactly what that number is, but there's this direction. If we looked in these various directions that these dark arrows are in, we'd be looking through the disk of the galaxy, and we'd see a lot of dust. We'd see a lot of dust and a lot of stars in these directions. And if we tried to see other stuff in this direction, if we're looking directly toward the center of the galaxy, we're not going to see much. There's a lot of thick dust in here. We're not going to see much beyond that direction. But if we looked upwards, in a sense, kind of out from the galactic plane, it's very open. There are fewer stars up in that direction. We can certainly see stars in those directions, and those are stars that are part of the galaxy, part of the Milky Way galaxy. But we'd be able to see a lot of other things, a lot of other galaxies, a lot of other, mainly galaxies that are much further away beyond our Milky Way galaxy. So when we think about what the sky looks like, just kind of going back to imagining that you're standing outside looking at the sky and not thinking about the Earth as one big ball, there are a few other reference lines that are useful for what we call your local sky. And so when you're standing at wherever you are, whether you're in Des Plaines, Skokie, Chicago, Gary, Indiana, wherever you might be, when you look straight overhead, that point straight overhead, of course, is not the celestial pole, but it's called the zenith. Right? That point directly overhead is called the zenith. If you are standing on the north pole of the Earth, then yeah, this point directly overhead would be the zenith as well as the north celestial pole. And then if you drew a line from your feet to directly south, right, and then you took that line and you drew it on the sky all the way up to the zenith, and then back down to the directly north direction, that line is called the meridian. And that's a good reference line for where objects are located. Are they to the east of the meridian, to the west of the meridian? So here's a star that's located right now a little bit to the east of the meridian. And we can think about its direction relative to the meridian with an angle. And we call that, right now we could call that direction just like southeast. But we could give it a direction like 20 degrees east of the meridian. So this angle in here would be 20 degrees roughly for that particular star. But as time goes on during the day, that star is going to move. It's going to come across this way. At some point it's going to be straight south. It's going to be on the meridian. And later on, it's going to be over here, and eventually it's going to set in the west somewhere, the western sky somewhere. And so the position of stars as the night goes by changes. At least they change in terms of this direction, this sort of east-west direction, kind of analogous to longitude on the Earth. Right? This is like a longitude on the sky, and we'll talk a little bit more about those angles and stuff later. But this other direction here, coming up from the horizon to where the star is located, we can measure that as an angle as well. In this case, it's 60 degrees. That's called the altitude of the star. So the zenith is the point directly overhead. This meridian is the line, just an imaginary line that goes from south to the zenith to north. And then we can measure the location of a star or a planet or anything on the sky using a direction that's sort of east or south or west or north, as well as an altitude, sort of like an angle above the horizon. And of course, that does change if the star is rising and setting. Okay. So we're going to be interested in measuring how big things are. how big is the moon? How big is the sun? How big is a galaxy? And so on. The moon is pretty big. The moon is actually about the size of the United States, roughly, across. But it certainly doesn't look that big when we look at it, because it's pretty far away. So we use angles to measure the sizes of objects, because maybe we don't know how far away they are, but we know that they have some size to them, but we can't measure that size directly. We can't take a ruler and put it across the moon, because we're not by the moon. But we can look at it and we can say, what kind of an angle would I draw if I drew a line from my eyeball to one side of the object, and then another line from my eyeball to the other side of the object? There would be an angle in there. We call that the angular diameter of the moon. And the moon is about 1/2 degree. And the sun is about that same size as well. And they vary slightly, because the moon is slightly different distance from the Earth at different times, and so is the sun. And then we can also look at stars. If we draw a line from our eye to a star and then to another star, we can talk about the angular distance between those two stars. And or across a whole constellation even, 6 degrees in this example here. So some approximate things that you could use to measure angles. If you were to hold your hand at arm's length, one finger, as you see it from your eyeball to your extended hand, one finger spans about an angle of 1 degree, roughly. If you put your finger up against the moon in the sky, your whole finger would cover the moon. It would cover the moon about, it'd be about twice as big as the moon. If you put your whole fist against the sky at arm's length, it would cover about 10 degrees. If you spread your fingers out and just spread your fingers out and went from your thumb to your little finger, that would be about 20 degrees. And that's a decent approximation. And yeah, some people have bigger hands, some people have smaller hands. Some people are taller, some people are shorter. So it varies a little bit, but that's a pretty good approximation. You can get a rough idea of the sort of angular distances between objects. So this gives you a little bit more information about angles. You've probably heard of degrees before, but you may not have heard of arc minutes and arc seconds. What a degree is, of course, is there's 360 degrees in a whole circle. It's like a little tiny slice of pie. There are 360 little tiny 1-degree slices in a whole pie. But you can break this down even further, and you can say, if I zoom in on this 1 degree, I can break it down into 60 little tiny slices. And so this kind of zooms in there. This is 1 degree. I've expanded the angle a little bit. We've divided it up into 60 little pieces. So a little tiny slice down here would be about what we call arc minute of an angle. But we can make that even smaller, make those slices of pie even smaller, and slice up that 1 arc minute into 60 pieces. Each one we call an arc second. So 1 degree is 60 arc minutes, and 1 arc minute is 60 arc seconds, we call it. So using this angular measurement of an arc second, we can really use that to really measure small distances on the sky. And that's useful especially for looking at things that are very far away, and hence they're very small. So this again shows a calculation, a way that you can look at calculating angular size. In order to know the physical size, the actual real physical size of something, we do need to know its distance. If you don't know its distance, its true distance, you can't know exactly how big it is. All you can talk about is its angular size. And this conversion, there's 360 degrees divided by 2 pi, that's a way of converting angular measurements between degrees and what are called radians. The radian is another way of measuring angles. So this is a good, useful calculation. In Physics 115, if you're watching this here in Physics 115, this isn't something you're going to have to use too much, but it's a good idea to know that. What you really need to know is that in order to use these angular distances to measure the size of an object, you need to know its actual distance. Otherwise, you have no idea how big the object actually is. If you're in Physics 120, then this is something we're going to use in some of our labs. So this is a useful thing, and we'll practice it in some activities during one of our meetings. So rising and setting, if you watch the video on Introduction to Stellarium, the software, planetarium software, I talked a little bit about this. But why do stars rise and set? Well, again, everything moves because the Earth is rotating. And, things are moving anyway, but the main motion that we see from night to night is because of the Earth's rotation. So if we stood on the North Pole, we stood there, then we would look to our horizon, and our horizon would kind of be the same as this celestial equator, this plane. And as the Earth rotates, it appears as if the stars are going around like this. Okay, and so everything would just go around the north celestial pole. And in fact, we would never see anything rise or set. Everything would always have the same altitude above the horizon from the equator. But if you look in a different place, this picture here is from a different latitude. You see there's all the stars are going around the north celestial pole here, going in this counterclockwise sense. But there are some that are rising and some that are setting. Many of them are rising and setting. These stars in here are not going to rise or set, but these stars over here certainly come up above the horizon. They go back down into the horizon. So here's another view from a different angle. If I'm not on the North Pole, but rather I'm at, maybe 42 degrees around Chicago or so, my horizon, if you think about a plane extended from your feet, if you look outward in all directions, your horizon is this plane right here. As these stars rotate around because of Earth's rotation, if we think about these stars rotating around, this star right here just touches our horizon over here, but it rises high above our horizon over here. And then it comes back down. This star here rises high above our horizon, but eventually it comes along and it sets. It touches our western horizon over here, goes across sort of underneath our horizon, comes up in the east, and rises up again the next night. So these are stars that rise and set, whereas this star is a star that doesn't rise or set. It's always above the horizon. Something that's always above the horizon we call a circumpolar object, a star or a constellation or something like that. And then there could be some stars that are on the southern part of the sky. If we're in the north, there could certainly be stars in the south that never actually rise above our horizon. We can just simply never see them. We'll never see these stars down here. So we're going to talk about coordinate systems on the sky, but it's good to remember coordinate systems on the Earth. So we have an equator, and we measure latitude relative to the equator. Latitude is an angular measurement. As you go from the equator up to the North Pole, it goes from 0 degrees, 30 degrees, 60 degrees, 90 degrees at the North Pole. And then you could go downward to the south. That would be 30 degrees south, 60 degrees south, and 90 degrees south would be on the South Pole. So those are sort of up and down measurements, latitude measurements. And then longitude are the directions along the equator. 120 degrees west, 90 degrees west, 60, 30, etc. And there's a place that's defined as 0 degrees longitude. That's a special location. It's called the prime meridian. And it's that location that astronomers just use as a reference. Really, everybody uses it as a reference, mainly for measuring coordinates on the Earth. So these pictures we saw a little bit before. Again, you're at the North Pole. If you're at the North Pole, everything just goes around the sky. Nothing ever rises, nothing ever sets. But there's half the sky that you cannot see, the southern portion. If you're, in this case, you're on the southern hemisphere, your horizon is this line that's, again, kind of perpendicular to your body. It sort of cuts through across your feet there. And your zenith, your upward point, where you're looking up, is in the southern hemisphere here, the southern part of the celestial sphere. So there are stars in the north that barely come up above the horizon and go down and set there. And there would certainly be other stars we could draw that would never rise or set for somebody in the south. And other stars that rise and set and go quite high and come back down again, depending on where you're located. All right, so notice, though, that as we're looking at this, we can't see the north celestial pole, but we can see the south celestial pole. It is above our horizon, 34 degrees in this case. And so we could see stars going around the south celestial pole. We'll look at a little animation in a second. But it's nice, at least for us, that we live in the north, because there is a star that's very close to the north celestial pole. It's called Polaris. And it's that star that appears to never move. It does move a little bit, but it's a good reference point for where the north celestial pole is. That is actually going to change over the next few thousand years. That star will no longer be at the north celestial pole, and we'll talk about why that happens later. So this little animation, we'll look at it. This little figure, we'll look at an animation of this in a second. But it shows the north celestial pole right by that star Polaris, and as the night goes on, everything seems to kind of go around that star, right? In the south, all the stars go around. They go in the opposite kind of clockwise sense, but they all seem to be going around a point over here. But there isn't a nice, precise, distinct star there. It's kind of just an empty spot for the south. So that figure that we can animate is here. So this shows the Big Dipper that we're looking north, about 10 p.m. Here's the star Polaris. And you can find the star Polaris if you look for the Big Dipper, and you take these two stars at the end of the at the end of the cup part, the ladle sort of part of the Big Dipper. They point toward the star Polaris, and Polaris is at the end of the Little Dipper. And usually it's hard to see these stars here in the Little Dipper. You can often see these two and Polaris, but it's hard to see these guys here. But these two stars of the Big Dipper point toward Polaris. And if we let time go by, everything rotates counterclockwise around the star Polaris. And in fact, Polaris actually does move a little bit too. It isn't perfectly stationary. Polaris is often called the North Star, and it is not the brightest star in the sky. That's a misconception. If we look south, everything's going to go this way, clockwise around the South Pole. And there isn't an actual star there. I mean, there might be a dim star very close to it, but they're hard to see. They might be more dim, but there isn't a nice bright star, fairly bright star like there is in the north. But everything goes around that south celestial pole as the Earth rotates. One last thing in this section, as we go around the sun now, as we go from day to day, from February to March to April to May and so on, the stars that we can see at night change. So the reason why that is if you imagine the Earth at one particular location, this is around August 21st, during the day you can look at the sun in this direction, and as the Earth rotates, we don't move very far on the orbit, but the Earth will make one complete rotation as we move just a little bit along this orbit, about 1 degree. And so every day, if we look toward the sun, we'll of course see the sun. If we could turn the sun down so we could see stars beyond it, we'd see these stars over here. The sun would be in the constellation Leo, and we could see these stars over here. And if we look during the night away from the sun, we'd see these stars over here in the constellation Aquarius, as well as other constellations nearby, Pisces and Copernicus and so on. If we let time go by, September, October, November, December, if we were in December and we looked toward the sun and tried to turn the brightness of the sun down to see the stars, we'd see these constellations over here, Sagittarius and so on. That would be during the day. At night, we looked opposite the sun and we see these stars, Gemini, Taurus, Cancer. We see those stars during the nighttime. So the reason why we see different stars at night is because we are going around the sun. And to see stars at night, you have to look in the opposite direction from the sun. And so throughout the course of the year, during the night, we can see all the different constellations of the zodiac, as well as all other constellations that are visible from our latitude. So in summary, we can see, our naked eye can see about 2,000 stars. There's a lot more than that, but those are about the stars that we can see with our naked eye, the ones that are bright enough for us to see. So you look at the sky and you might think, wow, there's millions of stars out there, but really the naked eye can only see about 2,000 stars. And then we use, on our local sky, we use these directions, these measurements of altitude and direction to measure a sort of an angle and a direction for an object in the sky. And then the stars rise and set because of the Earth's rotation. And then, of course, the constellations that we can see on a given night depends on the time of the year, because we have to look opposite the sun in the other direction from the sun to see the stars at night. And that direction changes as we go around the Earth, around the sun. So one last little animation here. Whoops, there it is. So these are, I'm getting these again from the study area of Master in Astronomy. So this one here is an animation of that figure going around the sun. Let me just expand this a little bit. So here we are. Here's the Earth right now. If we're looking toward the sun, we can see Taurus and Aries. And so you can see here's the sun, there's Taurus, there's Aries. And as we let time go by, the Earth is going to go around the sun. And now if we look toward the sun, we can see Cancer and Leo, Virgo, Leo, Cancer, Gemini, and so on. If we can switch views up here, we'll be looking away from the sun. So now we're looking in this direction at night, which is typically what you do. And you can see Aquarius, Copernicus, Sagittarius, Pisces, and so on. Let the Earth go around the sun a little bit more. Now we see Aries, Taurus, Gemini, Cancer, Leo, Virgo, Libra, and so on. And so this is why, again, the stars, the constellations that you can see, the prominent constellations you can see, change throughout the year as the year goes by. So send me an email if you have any questions, and I encourage you again to go to the Chapter 2 study area for under Mastering Astronomy and go play with these interactive figures. There's a lot of good ones, and I'll use more of them in the next few videos that I do. Have a good day.